All right. Good morning, everybody. As I mentioned, I'm going to go through some guided examples dealing with perfectly elastic and perfectly inelastic collisions. So far, in the notes, you've just been using the regular conservation of momentum formula to kind of solve all the problems. And you may have seen that in some cases, like in perfectly elastic collisions, um, the math can get kind of tricky and annoying because you end up having to um, use linear systems and substitute an equation into the other to solve it. So today what I'm going to do is look at a couple of difficult problems and a couple of shortcut formulas that you can use to kind of make your life easier. So the first thing we're going to take a look at is perfectly inelastic collisions. So in an inelastic collision, right, energy, kinetic energy is not conserved. Momentum is always conserved in every situation, but in inelastic collisions, momentum is not conserved, and perfectly inelastic collisions are where two things collide and then remain stuck together. So when that happens, okay, we can make use of this version of the formula. Okay, so it's kind of a rearranging of the conservation of momentum formula, and we can do that because they have the same final speed. Okay? So they have one combined speed, so VA prime and VB prime are the same, so we can just replace it with one. Okay? So this is an equation you can use. What we're going to look at today is what I would consider probably an iconic conservation of momentum problem. And what we're going to do is we're going to take a look at what's called a ballistic pendulum. So before we had kind of better technology, okay, this was a tool that was used to measure, how fast, like a high-speed projectile, like a bullet, would go. So what would happen is you would have a wooden block hanging on a string. You would fire a bullet into the block. Okay? The bullet would embed itself in the block, creating an inelastic collision. So these things become one object, and then the box and the bullet together would swing up to a new height. And using this information, okay, you can figure out how fast the bullet was going. Okay? So in this, because it's an inelastic collision, the kinetic energy is not conserved in the collision, but the momentum is. However, once the bullet is embedded all the way and they start acting like one object, so once the bullet is embedded in the block and they start moving together, then the energy is conserved, right? Uh, when the bullet is deforming the block, right, a lot of energy is lost there. So energy is not conserved from before the bullet hits to after the bullet hits, but momentum is. Once they're acting as a single object, the bullet is no longer, once the bullet is stationary inside the block, they move together as one. From there, energy is conserved. And basically, we have to use this conservation of energy and conservation of momentum separately in order to solve a problem like this. So let's take a look at one and see it with the numbers. See if that helps. Okay. So we have a bullet of mass 8.7 grams. Okay, so we have the mass of our initial object. And a wooden block with a much higher mass. So bullet gets shot into the block, embeds itself in, and then the bullet and box together are going to swing up on the pendulum, and they are going to swing up to a maximum height of 6.2 centimeters. Okay. What is the initial speed of the bullet? So we're trying to find how fast the bullet is going. So what we're going to do is we have these two objects that are working together, okay, and we know how high they go. So based on how high they go, we can figure out how fast they were moving when they were moving together. And once we know that speed, we can then use conservation of momentum to figure out how fast our projectile, in this case our bullet, was going. Okay? So we're going to start with conservation of energy. right? The energy at the beginning of the swing is the same as the energy at the end of the swing. So at the beginning of the swing, it is all kinetic. At the end of the swing, it is all gravitational, right? So once the bullet is embedded and the objects are swinging together, okay, you have all kinetic energy until it swings up to a maximum height before swinging back down. So we're turning all of our kinetic energy into gravitational potential. Okay, and in this case, the masses would be the combined mass of both objects. Okay, but in our equation here, the masses cancel out, so we don't even need to worry about that. Okay. So we get these values, and by multiplying and simplifying, okay, we get a velocity. Okay, so this velocity that we found is the same as the v prime in our conservation of momentum. So we have the individual velocities of the object at the start, and then we have the combined velocity together. Because even when energy is not conserved, momentum is. So this v that we found is really our v prime, okay, that we can use in the other equation. And we also know that vb is 0. The initial speed of the block when the bullet is moving before they collide is 0. Okay, so now we can use this shortcut equation that we just picked up. Okay, so we can take this equation and use it to help us find the initial speed of the bullet. Okay. This is 0 because VB is 0. So now we can start populating our numbers into here. Okay, so we can simplify this a little bit. Okay, and when we multiply this up to the other side, whoops. Okay, so we divide that out and we get that the speed of the bullet is approximately 660 meters per second. Okay. So this shows how we can use this short form equation, okay, the shortcut equation, when dealing with a perfectly inelastic collision. So when something hits something else and they get stuck together. In this case, the bullet got embedded in the block of wood. Sometimes it might be two cars crashing into each other and remaining stationary, or the example in the notes was two people were skiing, hit into each other and started moving together. Okay, so this is an inelastic collision, and the ballistic pendulum I would consider kind of an iconic problem for this unit because it combines conservation of energy and conservation of momentum into the same problem. So definitely make sure that you know how to do a problem like this. Okay. The next one we're taking a look at is perfectly elastic collisions. So up until now, in perfectly elastic collisions, right, things bounce off each other and go the opposite ways. And not only is momentum conserved, but kinetic energy is also conserved. So in these ones, so far, the way we've been solving them is we've been taking our equations for momentum and energy, and we've been subbing one equation into the other and doing kind of like a linear systems thing and the math can get really messy in those. So what I'm going to show you today are two equations that we can use that just make life easier. Okay? So first we have, so what this does is we have two objects that crash into each other and bounce off. And these are equations that can be derived from the fact that momentum and energy are both conserved at the same time. So VA prime, the final speed of the first object, okay, is going to be based on this equation, and the final speed of the second object is going to be based on this equation. Okay. So one key thing that you need to be aware of for this equation to work, these equations only work when VB is 0. So you have one stationary object, you have one moving object, they hit and they have a perfectly elastic collision. Okay, so they only work if VB is 0. So the question is, right, we want to kind of make use of these. These equations are much simpler to use than solving systems of equations. But what do we do in the case where both objects are moving? So that's what we're going to take a look at here. So we have two objects, a mass of 0.8 kilograms, and it is initially moving at 8 meters per second east, has a head-on collision with a 0.40 kilogram ball that is moving at 6.5 meters per second west. If the collision is perfectly elastic, okay, so kinetic energy is conserved, okay, what is the velocity of each ball after the collision? So we need VA prime and VB prime. So we need to figure out the final velocities of both objects. Now, traditionally, what we've been doing is going through and using systems of equations to solve this. And I mean, you can do that, but the math gets kind of messy and involved, and it takes a lot of time. So what I would like to do is I would like to use these equations because they're much easier to deal with, much easier to use, and you get the answer much quicker. And also, it's harder to make a mistake because the math's easier. But they only work when VB is 0. VB is not 0 here. So what I can do is I can force it to be 0. So what I'm going to do is I'm going to make a change to both speeds, and then at the end of the problem, I'm going to have to change it back. Okay? So I'm going to say for this problem, east is positive, west is negative. Okay, so VA is 8 meters per second, and VB is negative 6.5 meters per second. So what I'm going to do is I want to make one of these 0. So what I'm going to do is VB, I'm going to make that 0, right? Because this equation only works if VB is 0. So I'm going to make it 0 by adding 6.5 meters per second. And I'm going to do the same to the other speed as well. I'm going to add 6.5 to both of these. What I'm doing is basically I am temporarily making one of them 0, so it'll work in the equation, and then I'm going to have to undo this step at the end. Okay? So that means that VA is now 14.5 meters per second, and VB is now 0 meters per second. So now that VB is 0, we can use those equations from the other page. We can use these shortcut equations. So VA prime, right, MA minus MB over MA plus MB times VA. So we get some really simple math here. So much simpler than dealing with solving systems of equations with squareds in them, where you have to multiply a lot of things out and cross a lot of things out. So the math here is significantly easier, right? I'm just plugging numbers into an equation to get an answer. So I get 4.8333 meters per second. Okay. And on the other side, okay, I can use the other equation, which is 2ma over ma plus mb times va. So just like before, I'm going to populate my equation. Okay, and again, VA, I have to use that adjusted version. Okay, so I'm not using the 8, I'm using the 14.5 that we made, the adjusted version. Okay, so we run this one through the calculator, and it comes out to 19.333 meters per second. Okay, so now we have our two answers, okay, that we get out of these equations. But we're not done the question yet. So because of this step here, where we had to make one of them 0 by adding 6.5, well, we need to undo that now at the end. So I'm going to take this and I'm going to subtract 6.5 meters per second. And here I'm going to subtract 6.5 meters per second. So that means VA is going to be negative 1.6667 meters per second. Or we can just say VA is 1.7 meters per second west. Okay. And then VB, 19.333 minus 6.5 gives us 12.833 meters per second. Or we can say simply VB is 13 meters per second east, because it was positive. So positive is going to be east, and negative is west. So you can get these answers the traditional way, right? You can solve a system of equations, okay, if you want to, okay? But that is going to be more difficult. It takes more time, and because of the way the math works, there's a lot more opportunities to make an error. So personally, I really like these equations. You should know how to do it the other way. Practicing complicated math skills is going to be important for anyone moving on in engineering, science, math, anything like that. But these equations can be helpful and useful. Okay. So remember, they only work if VB is 0. So if the second object has a velocity, we need to temporarily change it. Okay, so in this case, right, I used my signs. East I made positive, west I made negative, so negative 6.5. I fixed that by adding 6.5. Okay, so that gives me 14.5 and 0. Once I have VB equals 0, okay, I can use these little shortcut equations where the math is much simpler, much easier. I get my answers. The only thing I have to make sure of is because I made a change at the start, I need to make a change at the end. So because I added 6.5 into this step, I need to subtract 6.5 in this one. So hopefully that helps you understand these things a little bit more and makes the calculations for elastic, perfectly elastic, and perfectly inelastic collisions a little bit easier.